Assalamualaikum warahmatullahi wabarakatuh. So today I would explain about input-output architecture. Okay, during this lecture, I would introduce the external devices that is related to the I/O, and then the content of the I/O module, the functions, techniques used in the I/O devices, and then the I/O channel, and also lastly the external interface. The I/O subsystems include but are not limited to blocks of main memory that are devoted to I/O functions. So it includes buses that provide the means of moving the data into and out of the system. Control modules in the host and in peripheral device. It also include interfaces to external components such as the keyboards and disk. Cabling or communications link between the host system and its peripherals is also included into the subsystem. So the figure here shows how all of these components can fit together to form an integrated I/O. So in any case, for the I/O module, it must have an interface and then the memory, okay, to contain or to become the buffer. Also with the electronics that is connected to the devices itself. Okay, and in order to connect to the motherboard, okay, they must be connected through the cable. Either the connection is in one way or two ways through a device interface which is connected to the I/O module itself. We can broadly classify external devices into three categories. One is the human readable, which is suitable for communicating with the computer user, such as the screen, printer, and keyboard. Whereas the machine readable, okay, is suitable for communicating with the equipment, okay, such as magnetic disc, tape system, sensors, and actuators that is mainly used in the robotic application. Okay, and then for communication is suitable for communicating with the remote devices. Okay, in this case, such as network interface card or modem. Okay, where in this case we can communicate through the user itself or maybe to another computer or terminals. The reader may wonder why one does not connect peripherals directly to the system bus. So there are a wide variety of peripherals with various methods of operation. So it would be impractical to incorporate the necessary logic within the processor to control a range of devices. So imagine that if we have a lot of devices that is connected to the computer itself, so it will be impractical to embed it inside the processor to control the wider range of the I/O devices. Also, the data transfer rate of the peripheral is often much slower than that of the memory of processor. So it is impractical to use the high-speed system bus to communicate directly with the peripheral. On the other hand, the transfer rate of some peripheral is or faster than the memory or the processor. So again, the mismatch would lead to inefficiencies if not managed properly. Peripheral often use different data format and word lengths that the computer to which they are attached. So that's why they need the I/O modules. So in this figure that you can see, the I/O module has two major functions. One is the interface to CPU and memory, and then another is the interface to one or more peripherals. Okay, so when you look at your laptop, you may see that when you want to connect to your maybe your printer, okay, maybe your printer or maybe to the external projector, okay, external monitor. Okay, the port itself, okay, maybe the DVI or HDMI itself is the interface. Okay, is the interface for that cable. Okay, and then from that cable, okay, for in my case is I'm using the VGA, right? So this is like the interface, okay, the interface, and then which is connected to the cable. So from one end we need the one interface, and then from one end we need another interface. Okay, so that's why one is for the interface to the CPU and the memory, and then another interface is to that peripherals. So the interface to the I/O module is in the form of control, data, and status signal. Okay, data and status signal. So the control signal determine the function. The control signal determine the function that the device will perform, such as send data to the I/O module, like input or read, and then or maybe accept data from the I/O module, like output or write, or report status or perform some control function particular device, such as positioning the disk head, okay, the memory reader to a certain sector. Okay, whereas the data are in the form of set bits to be sent to or received from the I/O module. So remember, it is in a 8 bits or bytes. Okay, and then the status signals indicate the state of the device. For example, if the printer is ready or not ready. Okay, so that the device is ready for the data transfer. Okay. Control logic is associated with the device control, where the device operation in response to direction for the I/O module. The transducer converts data from electrical to other forms of energy during the output, and from other forms to electrical during the input. So typically during this transducing or transforming, okay, a buffer is associated with the transducer to temporarily hold the data being transferred between the I/O module and the external environment. So the buffer size may be between 8 to 16 bits commonly. Alright, the functions of I/O module consist of 5 categories. One is the control and timing, 2 is the CPU communication, 3 is the device communication, 4 is the data buffering, and then the fifth one is the error detection. During any period of time, the processor may communicate with one or more external devices in unpredictable patterns, depending on the program's need for the I/O. So the internal resources such as main memory and the system bus must be shared among a number of activities, including data I/O. So that's why within the control timing requirement, okay, the I/O function needs to coordinate the flow of traffic between internal resources and external devices. For example, the control of the transfer of data from an external device to the processor might involve the following sequence. First, the CPU will ask the I/O module to check the status of attached device, if it's ready or not. And then the I/O module will tell the status. Okay, and then when it is ready, the device is ready, CPU will request for data transfer to that I/O module. So the I/O module will gather the data and transfer back to the CPU. Okay, the preceding simplified scenario also illustrate that the I/O module must communicate with the processor and the external device. So processor communication or the CPU communication involve command decoding, okay, like read or write, and etc. etc. So the I/O module will accept command from the processor, typically sent as signals on the control bus. For example, the disk drive might accept the command read sector, write sector, or seek the track. Okay, and then each command will include the parameter that is sent to the data bus. Okay, the data are exchanged between the processor and the I/O module over the data bus. Also, because the peripherals are so slow, it is important to know the status of the I/O module. For example, if an I/O module is asked to send data to the processor to read, it may not be ready to do so because it is still working on the previous I/O command. So this fact can be reported. Okay, the status can be reported with the status signal such as busy or ready. Okay. Also, sometimes they want to report certain error conditions. Okay. The fourth one is the address recognition for the devices connected to it. Just as each word of the memory has an address, so does the I/O devices. Okay, so that's why when we want to refer to certain I/O device, we refer through the address. Okay. Okay, the third category is the device communication. Okay, I/O module must be able to perform device communication, which involve command, status information, and data transfer. An essential task of an I/O module is data buffering. If the transfer rate into and out of the main memory or the processor is quite high, but the transfer rate is lower for the I/O devices, okay, so it would be a speed mismatch. So it require buffering, okay, so the data will not tie up the memory timing or resources during the transfer operation. Okay, so I/O module must be able to operate at both devices and balance. Okay, balance the speed mismatch. Okay, finally, I/O module is often responsible for error detection. Okay, for um, and also report that error to the processor. So one type of error detection is like a paper jam, bad data. So sometimes they will pop up on the laptop, on your computers, right? Okay. So the figure here shows the general block or diagram of an I/O module. So the module connects to the rest of the computer. Okay, here to the system bus, and then another interface to the external device. Okay, also they have connection to a set of signal lines here, the control lines, the data lines, and then the address line. Okay, so data is transferred to and from the module. Okay, through through the buffer. Okay, in one or more data registers here. Okay, the data registers. So there may also be one or more status registers that provide current status information. The module must also be able to recognize and generate addresses associated, okay, with the devices it controls. Okay, so each I/O module has a unique address. Okay, or if it is control more than one external device, a unique set of address must be assigned to each of these I/O device. Okay, so finally, the I/O module contains logic specific to the interface with each device that it controls. An I/O module functions to allow the processor to view a wide range of devices in a simple-minded way. So there is a spectrum of capabilities that may be provided. Okay, so I/O module may hide or reveal the device properties to the CPU. Okay, so in order to support the multiple or single device. I/O module also control the device functions or sometimes leave it for the CPU. Okay, in any case, okay, sometimes it depends on the operating system decisions. For example, the Unix would treat everything as a file. Okay, so there are three I/O techniques possible for the I/O operation. One is the program I/O, two is the interrupt-driven I/O, and then the last one is the DMA or direct memory access. With program I/O, data are exchanged between the processor and the I/O module. The processor executes a program that gives it direct control of the I/O operation, including the sensing device status, read or write commands, and transferring the data. So when the processor issues a command to the I/O module, it must wait for the I/O module to complete the operation. If the processor is faster than the I/O module, which is true, so this would waste the CPU time. Okay, when the processor is executing a program and encounters an instructions that uh, related to an I/O device. For example, if you want to read data, if you require a user to enter input from the keyboard, or you want the program to display the output through the monitor, okay, that would require an I/O, right? So, CPU will execute that instruction by issuing a command to the appropriate I/O module. Okay, so with program I/O, the I/O module will perform the requested action, okay, and then set the appropriate bits in the I/O status register. Okay, so that's why they need to set the status bits, either it is a read or write, okay, and then the or ready, okay, or not ready, and then they perform the transfer data. Okay, so that's the purpose of the status bit here. So the I/O module takes no further action to alert the processor. So in particular, it does not interrupt the processor. Okay, so here you can see CPU checks the status bit periodically. Okay, until all the data until it is ready. Okay, and it is ready. So they would issue the read command to I/O module and then read the status of I/O module. And then CPU will check the status. Okay, so when it is ready, it will read the word from the I/O module and then write into the memory. Okay, so I/O module will not interrupt the CPU. Okay, so it is the responsibility of the processor to periodically check the status of the I/O module until it finds that the operation is complete. So the CPU may wait or come back later to check the status. Okay, to explain the program I/O technique, we view it from the point of view of the I/O command issued by the processor to the I/O module, and then from the point of view of the I/O instructions executed by the processor. So to execute an I/O related instruction, the processor issues an address specifying the particular I/O module and the external device and also an I/O command. So there are four types of I/O command that an I/O module may receive it when it is addressed by the processor. First is that command for control, used to activate a peripheral and tell it what to do. For example, a magnetic tape unit may be needed to instructed to rewind or move forward of the record. Okay, so this particular of command is specific to a certain peripheral device, and then test is to use to test various status condition associated with an I/O module, okay, and its peripheral. So the processor will want to know that the peripheral is powered on, or the status of the availability of that peripheral. Okay, so if there is any error occurred, okay, so that is for the test command. And then read and write. Okay, read and write causes the I/O module to obtain an item of data, okay, from the peripheral and place it to the internal buffer. Or in other case, for the right one, it will cause the I/O module to take an item from the data bus, okay, and subsequently transmit the data to the peripheral. Okay. With program I/O, there is a close correspondence relation between the I/O related instruction and the processor fetches from the memory and the I/O command that the processor issues to an I/O module to execute the instructions. So there will be many I/O devices connected through I/O modules to the system. Each device is given a unique identifier of for that particular peripherals or address. Okay, when a processor issues an I/O command, so the command will contain this identifier, or in this case, the address. When the processor, main memory, and I/O share a common bus, there are two modes of addressing that is possible. One is the memory map I/O, and then one is the isolated. With memory map I/O, I/O devices and memory would share the same address space. So the I/O devices would have its own reserve block of memory. Data transfers between I/O device to and from would look like the memory read and write. Okay, so it will look like a memory access from the point of view of the CPU. So this means that we can use the same instruction to move data from to and from I/O and memory, okay, using the load word, store word, or load by, store by. Okay, so there are a large selection of memory access command available because they are using the same instruction. Okay, as alternatively, the bus may be equipped with the memory read and write plus input and output command line. Now, the command line specifies whether the address refer to memory location or to the I/O device itself. So, they are using a separate address spaces. Okay, so for this case, they use a special command for the I/O. Okay, for this isolated I/O. So to activate it, they use a limited set of I/O command using this isolated I/O. So the problem with the program I/O is that the processor has to wait for a long time for the I/O module to be ready, or either ready for reception for the transmission. So the processor, while waiting, must repeatedly check the status of the I/O module. So as a result, the level of the performance of the entire system is severely degraded. You imagine that the CPU can do something else, but instead of, they need to wait. Okay, they need to wait for the I/O to finish. Okay, to be ready. Okay, so it needs to repeatedly check the I/O. Okay, so an alternative is for the processor to issue an I/O command to a module and then go on to some other useful work. The I/O module will then interrupt, okay, the processor to request service when it is ready to exchange data with the processor. So in this case, the processor then execute the data transfer as before and then resume its former processing. Okay, in interrupt-driven I/O basic operation, okay, so there are two views. One is from the I/O module. Okay, so for the input, the I/O module receive a read command. Okay, I/O receive a read command from the processor, and then the I/O module then proceeds to read data. Okay, proceeds to read data from an associated peripheral. Okay, for example, if the CPU needs a read data from the keyboard, so the I/O will check the status, okay, receive that read command, okay, and then proceed to read the data from that keyboard. Okay, so once the data has been transferred, okay, the module signals an interrupt to the processor here, I/O to the CPU over a control line. So the module then waits, okay, until its data are requested by the processor. Okay, so when the request is made, okay, the module places its data on the data bus, and then it's ready for another I/O operation. Okay, so this basic operation here includes from I/O view and also the CPU view. So the first is that the CPU will issue the read command to the I/O module, and then once after that, CPU will do something else. After that, the I/O module will get the data from the peripheral while CPU does the other work. Okay. Once the data is ready, okay, has been read, okay, it would interrupt. Okay, it will read the status of the I/O module. So I/O module would interrupt to the CPU. Okay, so it will check the status if there is an error condition or if it's ready. So when the CPU is requesting the data, then it will read the I/O will read the data from the I/O module and then transfer to the CPU. So the CPU will write the word into the memory. So if it's done, no, and then it will again ask again from the I/O. Right. From the processor point of view, the action for the input is as follows. CPU will issue the read command and then it will do other work. And then check for interrupt at end of each instruction cycle if there is some interrupt signal. So if it's interrupted, it will save the context or the current state of registers, process the interrupt and until it's finished, and then go back to fetch the data and store back the previous stage. Okay, so interrupt I/O is more efficient than program I/O because it eliminates the needless waiting. Okay, so when CPU request an I/O, it will leave after that until it goes back and then check if there is any interrupt. However, interrupt I/O still consumes a lot of processor time. Every word of data that goes from memory to I/O module or from I/O module to memory must pass through the processor. It means load word or store word must wait for the processor. Okay, must go to the processor. Okay, so the occurrence of an interrupt triggers a number of events both in the processor and hardware. Okay, so when I/O device completes an I/O operation, the following sequence of hardware and software event would occur. So first is that the device controller or other system hardware will issue an interrupt. At that time, the processor will finish the execution of that current instruction. Okay, and then it will save. Okay, it will save the current status of its own registers. Okay, after that, processor will signal the acknowledgement of the interrupt. At this time, processor will pushes the program status word and program counter. Also, other status, okay, other status of the program, the current program, into the control stack. After that, the processor would load new PC value based on the interrupt signals. Okay, here is from it will go to the processing from the software itself. Okay, it will save the remainder of the process state information. Okay, and then after this time, the process will be interrupt. Okay, the interrupt will be processed until it's finished. After that, they will restore the process state information by restoring the old PSW and PC to the next previous program. Okay, so both these forms suffer from the two inherent drawbacks. One is that the I/O transfer rate is limited by the speed with which the processor can test and service a device. Two is that the processor is tied up in managing an I/O transfer. So a number of instructions must be executed for each I/O transfer. So interrupt driven, although it's more efficient than the program I/O, can still require active CPU intervention of the processor to transfer data between the memory and I/O module. And any data transfer must go through the CPU. So we can say that the CPU is still tied up and because of the transfer rate is limited, so the CPU still needs to be get busy during this time. So to transfer data for a large volume, okay, another technique is more efficient, which is the DMA. Okay, so this is a typical DMA module diagram. Okay, it has data line, address line, and the control lines. Okay, so in direct memory access, the I/O module and main memory will exchange data directly without the processor involvement. Here, CPU would issue the I/O command to the DMA and then would do something else. Okay, so it will issue read block command to the I/O module, and then the DMA would settle it. Okay, would settle it, the exchange between the I/O module and the main memory. After it finished, it will interrupt to the CPU. Okay, so the CPU will read the status of the DMA module and then proceed to the next instruction. DMA module is capable of mimicking the processor by taking over control of the system from the processor. It needs to transfer data to and from the memory over the system bus. So in this case, it needs to make sure to use the system bus while the processor does not use the system bus itself. So when the processor wishes to read or write a block of data, it would issue a command to the DMA module by sending the DMA module the following information: whether to read or write is requested using the read or write control line between the processor and the DMA module. And then the second one is what's the address of the device involved communicated on the data line. And then the starting address of the memory block for data to read from or write to. Okay, communicated on the data lines also. Okay, stored by the DMA module in its address register. And then the fourth one is that it must contain an amount of data to be transferred. Okay, number of words to be read or written. Okay, then the processor, the CPU will carry on with other works. DMA controller will deal with this transfer, either read or write, and then after it is finished, it will send the interrupt when it is completed. Okay, so quite efficient, right? Okay, so for this purpose, when sending the data to and from, okay, so the DMA module must use the bus only when the processor does not need it, or it must force the processor to suspend the operation temporarily. So the process or the technique of suspending the CPU operation is what we call as cycle stealing. Okay, cycle stealing. So if it's not an interrupt, CPU does not switch contexts. But if it's interrupt it interrupt the CPU using the bus, so it means that the CPU is suspended just before it accesses the bus. Okay, but the processor will be slowed down. Okay, the processor will pauses. Okay, it only pauses, but not slowing down excessively like the previous two techniques. Okay, so not as much as the doing the transfer. It's only suspending for one bus cycle. Okay. So the DMA mechanism can be configured in a variety of ways. So some of the example is that this is the first example. All the modules, okay, I/O modules, memory modules, processor, okay, are sharing the same system bus. So the DMA module acting as a surrogate. Okay, this one is as a surrogate, like a copycat of a processor. It will use this program I/O to exchange data between the memory and I/O module through the DMA module. So this configuration will maybe inexpensive, but it is not inefficient, okay, because when the program control the program I/O, so each transfer of a word will consume two bus of cycles. Okay, second example is that the bus cycle can be cut substantially, okay, by integrating the DMA and the I/O function. So there is a path between, sometimes there is a path between the DMA and several I/O device, one or more I/O modules, which did not include the system bus here. So the DMA logic may actually part of the I/O module or maybe a separate module, okay, that controls one or more I/O module. Okay, the third example is that we connect the I/O modules to the DMA module using an I/O bus. Okay, so by using a separate I/O bus, okay, it reduces the number of I/O interfaces in the DMA modules to one and provides for an easily expandable configuration. Okay, so as computer systems have evolved, there has been patterns of increasing complexity and sophistication of individual components. We can summarize as CPU. First is that the CPU directly controls peripheral device. This is seen in the simple microprocessor control devices. Second, a controller of I/O module is added. So the CPU uses program I/O without interrupt. So with this step, CPU becomes somewhat divorced from the separated from the specific details of the external device interfaces. Okay, as the same configuration, okay, on the step 2, okay, is used, but now they implement the interrupt. So here, CPU needs not to spend time waiting for an I/O operation to be performed, thus increasing the efficiency. Fourth evolution is that the I/O module is given direct access to the memory via the DMA. Okay, it can now move a block of data to and from memory without involving the CPU, except at the beginning and end of the transfer. Okay, the fifth evolution is that I/O module is enhanced to become a processor in its own right. Okay, and contain specialized instruction set tailored for the I/O. Example, you have a graphic card that contains its own specialized GPU processor with its own specialized instruction set tailored for that graphic card. And then the sixth one is, the sixth evolution is that the I/O module has a local memory of its own. So a large set of I/O devices can be controlled with minimal CPU involvement. So the interface to a peripheral from an I/O module must be tailored to the nature and operation of the peripheral. So when you want to connect to a monitor, okay, so you need a interface. You need the interface that is tailored to the nature and the operation of the monitor. So there are two types of interface that we can have here: parallel and serial. In parallel interface, multiple lines connecting the I/O module and the peripheral, and the multiple bits are transferred simultaneously, just as all of the bits of a word are transferred simultaneously over the data bus. Okay, parallel interface, okay, has been traditionally used for higher speed peripherals such as a tape and disk. Okay, so this is a figure that shows that the inside or the block diagram of a parallel interface. Okay, so this is to the system bus that includes, okay, multiple lines, okay, of input data that connect to the system bus, and then they require some buffer inside of it, okay, so that it can be transferred out using a multiple lines to the peripheral. Whereas the serial interface only has one line that is used to transmit the data. So bits must be transmitted one at a time. Okay, usually they use it for printers and terminal. With a new generation of high-speed serial interfaces, parallel interfaces are becoming much less common. Okay, so this is a serial I/O interface block diagram. Okay, so it includes a multiple line, okay, of input to the I/O module from the system bus, and then to transmit out, okay, it only require one line. So this is the signature of a serial interface. Okay, as you may see here, okay, we have a serial port. Okay, if you look at your PC, sometimes they have a serial port with a different pin. Okay, so serial port DB9 male and then serial port DB25 male means that there are 25 pins on that port. So a PC usually comes with two serial ports, COM1, COM2, and one parallel port, or what we can call as LPT. So parallel port here, okay, is what we call as the LPT. On the back of the PC, the serial port are either two male DB9 connector or DB9 and one DB25, whereas the parallel port is a DB25 female connector. Okay, you may not see it anymore. Okay, because that's they are obsolete. Okay, and then we also have FireWire 400 cable, USB FireWire 400, and then FireWire 800. Okay, as an example for a serial interface. Okay, so that's all for this chapter. Thank you.